Hi all, my name is Lim Wei Jian, and we are from team 2526D0037 from the Semiconductor Production and Manufacturing category. Our project topic is Edge AI for predictive maintenance using feature selection and hierarchical inference. Our project title is Memory Aware Edge Artificial Intelligence for predictive maintenance using feature selection and hierarchical inference. There are some predictive maintenance challenges that we face throughout the project. In semiconductor fabrication, each machine generates hundreds of sensor signals, but in our dataset, 591 sensors per machine. However, predictive maintenance faces four major challenges. The first one, high dimensional sensor streams create heavy memory and latency costs. And the second one, edge devices are resource constraints so that the devices have limited SRAM and DRAM. Thirdly, failure samples are rare and highly imbalanced. And the last one, noisy and redundant sensor signal reduce learning effectiveness. This means that deployment feasibility is just as important as detection performance. For the deployment constraint in real industry, AI cannot replace PLC system. Instead, AI must be retrofit ready and operate alongside deterministic control loops. From a hardware perspective, we face the memory war problem where memory movement dominates computational costs. Therefore, any scalable edge AI must be memory aware, latency sensitive, and deployment compatible. This leads to our central research question: how to build a memory aware and scalable edge AI model. Our proposed solution is a dual design strategy where it is feature selection for memory reduction and hierarchical inference for conditional computation. The first one, feature selection, we reduce dimensionality from 591 sensors to 24 features for level 1 and 70 features for level 2. This cuts memory footprint by approximately 88% while removing redundant sensor noise. Second, the hierarchical inference. This consists of two-stage pipeline, where level 1 performs fast anomaly screening and level 2 activates only when suspicious patterns are detected. This conditional computation structure reduces unnecessary processing while preserving detection quality. And the dataset we use to train our model is the SECOM dataset we found online. And it consists of total 1,567 samples that consists of 1,463 past data and field data with only 104. This dataset is multivariate, chronological, and imbalanced, closely reflecting to real industrial environments. For the time-safe evaluation strategy, we split into three sets, which is train, validate, and test. For the train, we use 736 samples for the past data, and for the validation, we use 298 samples. And for the test, we use 471 samples from the most recent data. And there is no future leakage. Each model is trained only on past data and validated on future segments. This setup mimics real predictive deployment scenarios. And our data pipeline is two-stage anomaly detection architecture, and it consists of two levels. Level 1 is lightweight screening, where 24 selected features only, fast anomaly detection, and initial suspicion filter. Besides, the level 2 is the expanded analysis that consists of 70 selected features with deeper anomaly refinement and only activated for suspicious cases. Both stages uses isolation forest trained only on past sample. Finally, anomaly scores are aggregated into sliding windows to capture degradation trends rather than single point noise. So to study the aberration, we use four variants for the benchmark configuration. The first one, the baseline model, is without both feature selection and hierarchical inference. The second one, only feature selection, and the third one, only hierarchical inference. And the last one is the optimized model, which integrate both feature selection and hierarchical inference. There is also our proposed solution. This aberration study allows us to quantify the impact of each design decision. Next, I will pass the next session to Wei Xuan. Thank you.
Hi, I'm Wei Xuan. So I will be explaining the window level detection performance. So at the window level result, it's clearly shown that there are two groups of performance. So as you can see, the baseline and also the hierarchical only model shows identical performance, which with a identical score of 0.3471, which is terrible. So this indicates that the hierarchical structuring alone does not improve the anomaly discrimination without reducing the feature space. So in contrast, feature selection and also optimized configuration actually show a better score or with a score of 0.5992, which improved by 72% as compared to baseline variance. So this confirmed that the feature selection is actually the primary driver of the detection enhancement. So moving on, I will be explaining the detailed result, window result of our optimized model. So as you can see, our optimized models can achieve a ROC score of 0.5992, while its recall achieved is actually surprising because it is highly comparable to other variants, which means that there is no missing failures, which is something that we desire in real fabrication environment, because missing failures can be costly. So in predictive maintenance, maximizing recall is actually uh, essential because we do not hope that there is any miss failures, because it can increase the operational cost significantly. So as you can see, hierarchical fusion actually enhances the sensitivity without sacrificing ranking discrimination. So moving on to the edge efficiency performance. So we are comparing baseline and also optimized variants. So looking into the inference latency, we can see actually the optimized models improve, possess a better performance in terms of the inferencing rate by with a performance of 37 reduction as compared to the baseline model. And other than that, the data movement is also reduced if we adopt optimized configuration. So as you can see, the memory sent from the models reduces by 9%, and the memory sent from the sensors to the models reduced significantly by 43%, which is something desirable. So this improvement shows that the feature selection actually can reduce the memory movement and also enable a more energy efficient computation. This enable energy efficient edge deployment. So I will highlight some of the key contributions, which is first, the feature selection actually improved the detection performance by 72%, while the hierarchical fusion actually promotes energy efficient data movement by a 43 reduction in the data movement from the models to the other system of the machine, while enabling lower latency, which allow the model to be deployed at the edge level. So next, I will be highlight some of the limitation we face during our project. So the first limitation will be limited field samples. So to be frank, the data set of our project is not huge, so we cannot validate the model performance using many field samples, meaning that the model may achieve or may produce good scoring in terms of recall, but it may not be it may not behave similarly when we adopt the model in real manufacturing environment where failures are mostly random and unpredictable. Next will be the future work that we can implement in our future study to enhance our project. So first will be the conditional L2 execution enhancing, which basically we enhance the rules of how our level 2 inference is triggered to enable a more efficient inferencing. Next will be improving sensor level explainability by our model, which we try to improve, or we try to strengthen the communication between the models and also our engineers to understand the failure trains or the failure mode so that they can identify the root cause better and perform troubleshooting immediately. Lastly, we can implement or we can try to integrate federated learning for a more economical deployment. So in short, we are not saving the memory capacity, we are saving the memory movement. So with smart feature reduction, the anomaly separability actually improve, while the memory traffic and also the inference latency can be significantly enhanced. So our project actually demonstrated that with the feature selection is actually one of the main performance contributor, while the hierarchical inference allows conditional computation by reducing unnecessary processing. And it also allows the model to achieve comparable window level sensitivity in the optimized configuration. So in short, the future of predictive maintenance does not lie in a larger or a more powerful models, but it lies in smarter architectural design. By combining memory-aware feature reduction and also hierarchical inference, we deliver an edge AI framework that balances between the performance, scalability, and also the feasibility. As we state, we are not saving the memory capacity, we are saving the memory movement. That's all from our group. Thank you.